All right, so again, we did the first 2 lessons of chapter 5. So we had our Pythagorean theorem, special right triangles. Then we're going into chapter 8, and this is a lesson that kind of could have gone in our last unit because it's using right triangles, but since everything's about right triangles each unit, we're like, we'll just keep it in this one. All right, here's the first one. It says the altitude to the hypotenuse of a right triangle divides the triangle into 2 triangles that are similar to the original triangle and to each other. All right, so what are we talking about? First of all, how many triangles do you guys see in this diagram? 3, right? Does everyone see the big one? Triangle ABC. The theorem that they're talking about is they said there's an altitude to the hypotenuse. Actually, let's go here. This is what they're talking about. Oh, let's move everything a little bit more than I want here. This is the altitude to the hypotenuse that they're talking about. Okay, that's what they're trying to describe. And when you do that, you get 2 smaller triangles, correct? And you get, and we're going to redraw those real quick, so I advise for you guys doing the same thing. You're going to have triangle, and I'm going to try to draw a little bit to look kind of like where it comes from. Here's triangle ADC, and you guys agree with me? I'd have a right angle right here. And then we have our middle, I call that the small triangle. And then we're going to have our medium-sized triangle. Here we go. A little bit bigger, you can tell. And that's going to be C, D, and B. Now, so using the big triangle, ABC, and those 2 smaller triangles, I'm claiming all 3 are similar. All right, guys, what are the ways that we can prove triangles are similar? Side, side, side. What's another one? Angle, angle, similarity. What was the other one? Side, angle, side, similar. All right, does anyone see actual physical side links with this? Anyone? No, there's no physical side links there. So I just threw out 2 of them. I'm having to rely upon AA similarity. Let me show you how cool this works. First of all, look at the big triangle. Okay, do you guys agree with me? I can mark B here because that's going to be one angle. And I'm going to go over here and mark A. And I know that angle A and angle B, do they add up to 90 because of the big triangles? Right triangle. Okay. Now, I'm going to mark those angles in the 2 smaller ones. Do you guys agree with me? A would have to be because of the reflexive property, also A. And would you also agree with me that B would have to be the same size here? Now, before I go any further, I already have AA similarity, but I want to go a step further here. Guys, if angle A in the small triangle, we already have it marked green, has 1 mark, what is angle ACD going to be marked? Is it going to be marked with 2? What do you guys think? Is that going to happen? Let me put it this way. What if this was, let's say 40 degrees? If this is 40 degrees, doesn't this angle over here have to be 60? So what would that leave angle ACD have to be? Does that also, not 60, let's say 50. I just did my math wrong. Shouldn't it be 50? Would that have to be 50 as well? Wouldn't this one have to be 50, which means this one would have to be what? 40. Now, I'm just worried, someone's like, where'd you get 40 and 50? I just made them up, okay? I'm just trying to make a point here. The whole thing is the angles, aren't they going to match up? And really, I have AA similarity, but really, I could almost have AAA similarity on this one. The thing is, because of the measure of angles and the reflexive properties of shared angles, I can prove that all 3 of these are similar to each other. So really, think about where these are going to go. I'm going to have this one here. And all I did is I just redrew it separately. But isn't that true? Like, literally, those are going to only be the measures of the angles that I have. Shouldn't I now be able to write a similarity ratio between them? Yeah. In fact, let's just do it real quick. First one, let's go to the big triangle first because I always think it's the easiest one to see. Let's go to triangle. Let's just go ABC. So I got triangle ABC. Now, again, I use the vertices. When I do similarity and congruency, I always use the vertices I can to match these up as much as possible when I'm working with it. So with that, if I go A has what mark? The green arc, is that right? So looking at the small triangle, isn't A also my green mark again? So would I also have A here? Then when I went to the big triangle, I went to the mark with 2. Well, in the small triangle, where's my mark with 2? C. And then what's left? C, and then I'm left with D. Do you see how I use the congruency marks to help me figure these out? So then, okay, let's go backwards. So if I go to ABC, I go from 1 mark to 2 marks to the right angle. So looking at the medium-sized triangle, what's going to be my 1 mark? This time it starts with what? I'm going with C. I got to go to 2 marks, which is C, B, and then I'm going to end with my right angle, which is D. Now, could I put these in any order that I want because we have the symmetric property of symmetry? I could put the small triangle first, the big one last, middle one. But you should be able to write these. Now, how do you know if they're right or not? If you matchy-matchy, do they match up correctly? And the cool thing is, if I'm doing proportions and stuff, could I pull out any 2 that I need? So let's try this with some triangles down below. This is where if you know you understand it at all, what we just did. All right, so it says write a similarity statement that compares all 3 triangles. All right, for a lot of people, what's the best thing you could do? Probably what? Redraw it. All right, so redraw it if you need to do that. I'm totally okay with that. So I'm going to redraw the medium-sized one right here. That's J, M, and K. And then I'm going to redraw the small one. That's J, M, and L. All right, so let's use colored marks to work on these. All right, so I'm working with angle K. I'm going to let that be 1 single mark, and that's going to be in blue. So do you guys agree with me? This one's going to be in blue? All right. Now, let's use a green one here. For some reason, I like green to do the 2 marks today. Wouldn't angle L be my 2 marks with the big triangle? Because I'm using the big triangle as my reference. Triangle KJL. Does that sound good? KJL. All right, so I'm going KJL. Well, that means this one's going to be 2, right? Does that mean this one's the 2 mark on that triangle? And then my blue one, I'm going to come back over here and get this one to be blue. So now, and you can even do it on physical diagrams if you're really good like that. I'm not really that great with that, so it's harder for me to do it. So I redraw it. But now let's see if we can write the similarity statement. All right, someone do it real quick for me. Name the big triangle for me. Emma, just name the big triangle for me. All right, she said KLJ. Okay, great. It's similar. Which one do you want to do next, the medium or the small one? Do the small. All right, so the small one's on the right. So she did KLJ. So she went from the blue angle mark to the green angle mark to the right angle. Everyone with me on that? So from 1 to 2 to the right angle. All right, so she started with the blue one. What's going to be in the small triangle? That's angle what? Because remember, this is our small one. Isn't that going to be angle J is going to have 1 mark? All right, then I got to go to the 2 mark, which just nice is what? Angle L. And then we end with our last vertex, which is going to be M, our right angle. All right, so now we're going to do the medium one. Okay, remember, go back to the large one. I go from 1 mark to 2 mark to the right angle. All right, to 1 mark, we're going to go triangle K. So we have our K going with 1 mark. Then I have to go to 2 marks, which ends up being what? J, and then I end with my right angle, M. What do you guys think? Doable? But could you see how you can get yourself confused with this? Some of you are like, I don't even need to redraw. I just need to mark my angle measures in. That's fine. Some of you might want to put physical numbers in instead of angle marks because you're making it up. You're just trying to write the similarity. No one's going to judge you if you picked a weird number or angle on this or not. It's just like so you can match the vertices, do what you need to do. So let's do this last one. Do you think we need to redraw this last one? All right, some of you are like, no. All right, here's the deal. Try it real quick. I'll redraw, but you guys see if you can do this to make them match. All right? Let's see if we can make these match. Let's go. All right. So I was like, this is hard. It's just hard because your eyeballs, I think, go bonkers looking at 3 different triangles, okay? It's just hard. All right. Someone name for me the largest triangle. What do you got? Triangle what? RTS. Okay, so we got triangle RTS. Great. All right, which one did you do next? Middle, small one or medium one? Medium. All right, some of you just have to go big. Okay, I understand. All right, we'll go medium one then. All right, so if we go RTS, that's 2 marks to 1 mark to the right angle, right? So 2 marks. What was the 2 marks in the median one? S, T, and then what? P. Perfect. All right, so what's going to be the small one then? All right, because we started with this one. We started with 2, right? So it'd be R what? RSP. Now, how do you know if you're right? What if you did yours in a different order? How do you have to check to see if you're right? This is the hard part. You just match to see if your letters go together. You literally have to play the matchy-matchy game. And you could have done it different. Remember, there's 6 different ways to name in one triangle. So yeah, you have to be really careful. The good thing is, you only have to name the 3 of them most of the time, once or twice on homework problems. Most of the time, we'll only be ever using 2 out of the 3 as we go. Make sense? All right, good. I'm glad you guys can see those because this will save a lot of hassle later. All right, you have a new term, and it's called the geometric mean. When you hear the word mean, a lot of times that means average. That's not the case in this, so you have to really know the definition. A geometric mean is a fancy math term that you get when you work with proportions. Now, if you guys will look with me real quickly on here, what are the 2 x's represent in that proportion, the extremes or the means? They're in the means location. That's why they're called the geometric means. And the reason why we use these a lot is with similar triangles. A geometric mean is the positive number, so here's the other thing, it has to be positive, where if I was to cross multiply and solve, it's the square root of AB. Now, a lot of people are like, what? I'm like, here, let me just show you. It's a lot easier to use proportions, okay? So if I'm looking for the geometric mean, let's just say I have 2 numbers, and they say find the geometric mean of each pair of numbers. So it's 2 and 8 are my 2 numbers. To do a geometric mean, all you'd have to do the following. 2 is to x as x is to 8. You put x in what location? The means. Can I cross multiply now? All right, so what do we get? We get x squared is equal to what, scholars? 16. How do I solve for x? I take the square root of it, and I do a plus or minus, but what does the geometric mean says it has to be? Has to be positive, so can I drop my negative? Yes, and so I get x is equal to, oops, I forgot my square root symbol there, 4, correct? That's it. That's what geometric mean is. It's basically finding if the means of a proportion are the same number, solving for the positive value of it. What do you guys think? Not too bad, is it? All right, so let's do another one. This is fun math because it's simple. All right, what's my proportion going to be? 10 is to what? 10 is to x as x is to 30. Cross multiply, you get x squared is equal to 300. Is that right? Okay, so I'm going to take the square root of it. Please make this easy on yourself, guys. What's the perfect square number that comes out of 300? 100, right? What's the square root of 100? Isn't that going to be 10 root 3? Yes, I want it to be that easy. Okay, 10 root 3. Okay, you guys go ahead and do the last one. You guys do the last one. My equal signs look like 2s all the time. Driving me crazy. Did you guys get x is equal to 6 root 2? Remember, the largest perfect square number that can come out of 72 is 36. So square root of 36 times the square root of 2, so it'd be 6 root 2. All right, what do you think about geometric means? Aren't those easy? Now, why in the world do we have to talk about geometric means? Because look, this theorem is so confusing, I don't even have you fill in the blank, people, okay? So I just want you to know, I love you enough not even to fill in the blank on this one. All right, here it is. So it's a corollary to the very first one. which means I'm using really the concept of similar triangles to set up proportions. It says the following. The length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. Yeah. Everyone got that? Let me reread that for you as your brains are like going, my head just hurts reading this. It says the length of the altitude, the hypotenuse of a right triangle, is the geometric mean of the lengths of the segments to the two hypotenuse. Basically, I'm telling you that this segment right here is a geometric mean. And this is what really the proportion you're supposed to understand comes from that. Because they're saying the following. Segment AD, actually let's use a different color highlighter there. Segment AD is to segment CD. Segment CD, so I'm going to put the AD here. See if I can get this, is to DB. So it's those three line segments. Basically, I'm supposed to be able to write proportion from it. Now, I have a nickname for this called the arrow through method, but I want to show you where this came from first. Okay, I want to show you where this came from first. Guys, this comes from the two smaller triangles, okay? So when I'm working with this, this is really a proportion formed. This is when I use the fact that the smaller triangles are similar. So I'm looking at the middle one and the small one, okay? And literally, you can even redraw this if you want, because we did this earlier. So A, D, C, and then you can do this one right here. And if you don't want to draw these out right now, you just want me to do it, that's totally fine. But you guys agree with me, this and this are going to happen, this and this, okay? Those would be my corresponding stuff, and that's really based off of our very first theorem that they work. And here's really what I'm doing. I'm using matchy-matchy right now. I'm doing the problem like this. I'm looking at the small triangle's leg, this one right here. So you're gonna sit there and say small triangle leg is gonna be to the leg of what triangle? The big triangle's leg. So this would be the, let's say the medium triangle leg. Right there, right? Small triangle leg to medium triangle leg. It's really the small leg of the small triangle to the small leg of the medium triangle. As, okay, the longer leg of the small triangle to, you guys agree with me, that's the longer leg of the middle triangle to the medium triangle long leg. Now this is how I've said this for years. Leg to leg, leg to leg. All right, it's the basically the idea. Now, wouldn't there be a nice way to have a shortcut of that and having to really think it all out? There it is. It's called the geometric means, and I call it the arrow through method. If you're given those two segments, two out of these three segments, if you really think that I'm arrowing it through, I'm going to use a red marker right here, excuse me. You start at AD, you go to CD. It's your geometric mean, so you repeat CD what? Twice, and then you go to DB. So let me show you what I mean. Go down to the problem right below here. I'm looking for X, okay? I know to use this method when I am missing one of these three. Remember we talked about it before, like here's my geometric mean. This is one of the legs of the small triangle, and then we know we're going to be corresponding to one of the legs in the big triangle. So you see how I'm still looking at those three segments even though they're not labeled that way? So using the arrow through method, because I know I could, as long as I have two of those three segments, I can set up a proportion every single time. I go like this. 2 is to 6 as 6 is to what? X. The geometric mean, right? That segment CD has to be what's repeated. So then it's just as simple, and I'm going to rewrite that so it's a little bit larger so you guys can see it. So 2 is to 6 as 6 is to X. Can I just cross multiply and solve now? And it's 2x is equal to 36. Guys, what's X going to equal? What do you guys think? Do you see how I almost prefer just an arrow through method than having to sit there and think, okay, leg of the small triangle to the leg of the medium triangle to the big leg of the small triangle to the big leg of the medium triangle? But it's still similar triangles. Yes, ma'am?
Will our triangles always be set up working like this? Or
Oh, don't worry. I have a lot more examples later. All right. This is just to get the idea across. All right, ready for your next theorem that will blow your mind? I call it the Mickey Mouse method. No one else ever sees it, or the snail method, but maybe you guys will be able to go there with me. All right. So with this one, here's a new one. It says the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle, the big triangle is what they're talking about, is the geometric mean of the length of the adjacent hypotenuse segment and the length of the hypotenuse. Did anyone just get completely confused by reading that? I see those hands, and some of you are like, my head. So you know what a good teacher does, right? I reread it, and you're supposed to be unconfused. So let me reread it just to see if it helps, right? And if I reread it louder, it makes it more understandable. Okay, you guys can all smirk at this point. I'll reread it, but then I'm going to explain to you exactly what it means, okay? All right, the altitude of the hypotenuse of a right triangle separates the hypotenuse so the length of each leg of the hypotenuse is the geometric mean of the length of the adjacent hypotenuse segment and the length of the hypotenuse. Okay, now, everyone your brain just got hurt, correct? So I want you to look. Do you notice there's two sets of proportions here? All right, let's look at one at a time, all right? So first one that we're looking at as we're talking about segment AC. So I want you to see this segment right here. No. I like you guys. All right, anyway, just know the method is really what I care for. What you're doing here is you're really using, for this first one right now, you're using the idea that the small triangle and the big triangle are similar. So the first one is really using the idea of this small little triangle on the left and the big triangle and the ones that are similar to each other. So are you guys with me? I'm just going to use that as my similarity statement. And this is how I'm going to be setting it up, okay? So on this first one, okay, we're going to use the fact that segment AD, do you guys agree with me? Segment AD is a leg of the small triangle, right? Now, doesn't that have to correspond to the leg of the big triangle? So remember, this is leg small to leg what? Leg big triangle, so small triangle to big triangle. Are you guys with me on that? So really, AD is going to correspond to which one? AC? Now, go back to the idea of the small triangle again. What is segment AC, though, in the small triangle? Hypotenuse of the small triangle, right? So guys, what's the hypotenuse of the big triangle? Yeah, this ends up being here, hypotenuse small triangle to hypotenuse big triangle. So basically, I'm just using leg is to leg as hypotenuse is to what? Hypotenuse. Now, how in the world do I show this? Now, I think I was creative as a teacher once when I came up with this method. My own daughter thinks I'm nuts with this. Okay, so humor me and act like you like my example. All right, guys? Remember how this starts. For this first proportion, so I'm just doing the first one, and I'm doing the one in green here. I'm going, the leg of the small triangle goes to the leg of the big triangle. So AD is to AC. AC is my geometric mean. So then I go, the hypotenuse of the small triangle goes to the hypotenuse of the big triangle. And I think that looks like a snail shell and a snail. What do you guys think? Some of you are like, Gregorson, I don't see it. Okay, half a Mickey Mouse ear. Will that work? Okay, like a Mickey Mouse hat? Okay, I'm dying here. But all right, just remember the arrows make the method of which direction you need to go, okay? But notice I didn't use CD in this at all. I went leg to leg, hypotenuse to what? Hypotenuse. Now, that's for the triangle on the left. And notice there's another whole proportion over here. So let's rewrite this proportion so we can see it easier. Let's go DB is to CB as CB is to AB. Okay, so what segment's being repeated, guys? CB. All right, so guess which two triangles I'm going to use for that one? I'm going to use the medium one and the big one, okay? So on this one, I'm going to be using, let's just do it over here, so that way we're all in the same thing. We're going to use the medium triangle and the big triangle this time. And I'm going to use exactly the same wording when I'm talking about this, because look where I start with. I start with segment DB. Well, isn't segment DB a leg of the medium triangle? It corresponds to the leg of the big triangle. So leg medium to leg what? big, as, oh, look, back to the medium, isn't BC the hypotenuse? So it's the hypotenuse of the big to, hypotenuse of the medium one to the hypotenuse of the big. So then it goes like this. It's exactly the same way of doing it. So leg to leg, hypotenuse to what? Hypotenuse. Now some people go, this is hard for me to see. All right, here's what I'm going to tell you. Redraw triangles and just set up proportions like you normally would. And just to me, that takes a lot of time. So let me show you an example of this, okay? And this is a very simple example, and then we get all complicated after that. I'm looking for x. The moment I'm looking for x, do you guys sit there and you go, okay, that's the small triangle side? Is that right? You guys with me on that? And if it's a side or a leg of the big one, this lets me know I'm using the idea of the geometric means for the small triangle and the big one. Okay, so let's set up a proportion this way. I'm going to use my snail. By the way, if you notice back there, do you see where I get the Mickey Mouse hat now? See the two ears on the side? Yes. Okay, it's cheesy, but it works. Okay, it's like the Mickey Mouse wizard hat. All right, anyway, moving on. I thought more of you were Disney than that. All right. Let's set this up. If I'm missing one of the sides, one of the legs of the big triangle, I know I'm using the small or medium and the big. So I'm using the small one on the left. So it's going to start like this. 4 is to what, guys? Yep. 4 is going to go to x, as x is going to go to, what's the whole thing? It's not 4 or 5. It's which one? 9, the whole thing. The snail. Like, make sure the snail is the whole body, the whole hypotenuse. Are you guys with me on that? Okay, Lauren, thanks for smirking at my bad example. All right, I appreciate that. So with this one, isn't this easy cross multiplying them? So I get here, x squared is equal to 36. Guys, what's x going to equal? Yeah, x is just going to equal 6. Now, I didn't ask for this, but could I go ahead and let's just do this anyway. I don't even think it's in my notes. What if I wanted to solve for y? What would I do if I wanted to solve for y? Can anyone set up a proportion for me that would work? I heard it what? 5 is to what? Yeah, 5 is to y as y is to 9. It's the other snail, right? So 5 is to y as y is to 9. So I get y squared is equal to 45. Take the square root of both sides. That reduces down to 3 root 5, I do believe. Does everyone see where I got 3 times the square root of 5? Because 9 times 5 is 45. What do you guys think? Is it doable? Now here's the other thing. If you're stuck and you can use the Pythagorean theorem, you have permission to do so. Because if I have two sides of a right triangle, should I be able to use the Pythagorean theorem to solve for a side? So understand you can use everything we've used so far as well. Just don't use a 30, 60, 90 on me, okay? Or 45, 45, 90 and we'll be good. Now this is a little bit more what your homeworks are going to look like. So you're going to be setting up somewhere anywhere between like 1 Pythagorean theorem and like 2 proportions or 3 proportions in order to solve this. So on the first one I started easy and you only have to solve for 2. All right. So right now pick which variable you guys want to work with first. Which one you want to solve for first? X. All right, if you want to solve for x first, that is one of the legs of the giant triangle, right? The big one. So is this going to use the snail method? Is this where I'm going to be using the medium triangle to the big triangle this time? All right, so if I do that, let's set this up. Isn't that going to be 12 is to what, guys? 12 is to x as x is to the whole thing, which is 16. All right, so I get x squared. Guys, what's 12 times 16? What do we get here? Do you guys get 192? All right, this can simplify out. This can simplify out. I'm looking at it, and I think it's 64 can come out. So I think it's going to be 8 root 3. But someone double check me real quick. Does 64 go into 192? Did I get it right? Okay, thank you. All right, so we got 8 root 3. Now, if you're really good at this, guys, honestly, could I use the Pythagorean theorem and solve for y using the small triangle on the right? You could. So if you did, guess what? Would you get full credit? Now, however, I just want you to use the proportion method right now. But the fact is, if you did that, as long as your radical was correct and it came out positive, would you be okay? And the answer is yes, you would get it totally right. So I want you to know that. But I'm also realizing if I'm looking for y here, I'm looking and I have that geometric mean in the middle of the two small triangles. So this is where I'm going leg is to leg as leg is to leg, right? So small leg to small leg, big leg to big leg of the two smaller triangles. So that's going to be the arrow through method. So for this one, I'm going to go 4 is to y as y is to 12. So I get y squared is equal to 48. Take the square root of that. Y is going to be, what does it simplify down to? Does 16 come out 48, guys? So shouldn't that be 4 root 3? Those are your two answers. All right, what do you guys think? Is this doable? All right, let's try this. Now you're going to start getting nasty looking ones like this, okay? And honestly, I have way too many examples on here that we will probably not get to today. So I'm trying to, and we're not going to get to. So you know what I'm going to do? For the sake of all of you, just so we get this done, on my off period, I'm going to finish videoing the notes so that way you guys have it for online. Does that sound fair? Okay, so I'll finish videoing that on you. You guys got the basics that you needed. I knew I had too much stuff on here, especially if I was going to go over the quiz today. But let's do that. So those of you who have early study hall, I'm sorry. This is going to have to be tonight's stuff probably, unless you can work on it. It's up to you.
Thursday tomorrow.
So you have Thursday scheduled tomorrow. So you guys can come in tomorrow at lunch too if you want. Sound good?